Thanks. I will present the work that has been done by José Antonio Jimenez Montero and collaborators from National Research Institute of Agriculture and from Polytechnic University at Madrid. Well, I will describe first the data and the methods, describing some details of the final methods that has been used, that is the R-busting method, and some results obtained with the different methods. For the data editing and quality control about the genotypes, the basic edits that were done was that all the SNPs that had missing information from more than 5% of the genotyped animals were eliminated. Also, those with minimum allele frequency less than 5% were discarded. For the Spanish population, because I will present some results from the original Spanish population with less than 2,000 genotypes, and then with the Eurogenomics reference population. For the Spanish genotypes reference population, we were using mainly version 2 SNPs, version 2 50K chip, but for the Eurogenomics population, there were mainly version 1. So that's one difference from both analyses, is that for the Spanish reference population, we finally came out with near 39,000 SNPs, and for the Eurogenomics population, it was quite less. It was around 36,000 SNPs. The main reason for this difference is because for the Eurogenomics reference population, we were using, well, they were using only common SNPs to version 1 and 2. For next steps, those all SNPs will be all imputed to version 2. Also, for Eurogenomics reference population, the chromosome X was discarded. It was also estimated the measure of linkage disequilibrium as the R square with a value of 0.24, that is similar to what has been calculated in other populations. The remaining missing SNPs were imputed with Beagle, fixing just the holes. And well, the final animals, genotyped animals that were available for the Spanish reference population was 1,797 genotyped animals and 22,300 for the Eurogenomics reference population. For the Spanish reference population, they were used the raw progeny proofs for 4 traits. That's for milk yield, fat yield, protein yield, and other depth. Then the basic validation procedure is as usual. There's a truncated validation where it establishes the reference populations with sires born previous to 2005, and it has a breeding value available in January 2009. That means for the Spanish reference population, it was around 1,500 bulls, and as I said before, it was the data used was progeny proofs. And for the Eurogenomics reference population, it was there was also a limit on the. It was asked to have at least 75% of reliability, and so the reference population was composed of 14,500 animals. And for these animals, they were their maize proofs were the regress. For the validation set, they were used the sires born from 2005 till 2007 that had progeny proofs in December 2011. And again, this is for the Spanish reference population, there were around 200 bulls, and for the Eurogenomics reference population, there were around 3,800 bulls. Again, for the genomic reference population, requisite was the reliability higher than 75%. The criteria used for analyzing the predictive ability were the accuracy measured by the Pearson correlation, and the mean square error, and the regression coefficient. Also, some results are shown for the pedigree index and Bayesian lasso just for comparison. Well, the method used, the final method chosen has been the R-busting. That is a modification of the busting algorithm, and I will describe just briefly about it. The busting is a machine learning ensemble method where it's an iterative process where in each iteration you apply a different model, and then at the end you have the final estimates are a combination of all the models estimates you have obtained in a different iteration. For the R-busting, it's a slight modification of the original busting algorithm that I will present now. Well, as I told, it's an iterative algorithm. Then in the first step, there's a random sampling of a subset of SNPs. From all the SNPs you have available, you make a random sampling of 1% to 5%, and this is the modification of the boosting algorithm, and that's the reason of the R-busting name. Then for these SNPs, for these 5% of the SNPs, you apply in this approach that has been used, you apply a simple regression, SNP by SNP, on the residuals obtained in the previous iteration. For the first iteration, you consider that the estimate that you have is the average of all the phenotypes you are using. And then from all this, you have all the regressions, the estimates that you have done for each of these 5% of the SNPs, and then you select the SNP that best describes these residuals based on the minimum square error. So in each iteration, you will be selecting one SNP only. The original busting algorithm in each iteration was testing or was applying this simple regression SNP by SNP, but to all SNPs. The reason for applying it only to a small percentage of the SNPs is just to reduce the computing time. At the same time, they did increase the number of iterations. That is, I think it's around 25,000 iterations. Then you, with the result of the estimate that you have obtained in this simple regression, with this SNP that has been selected, you update the prediction equations of the DGVs, but there's a detail that there's a shrinkage parameter so that you do not give total confidence to the estimate you have done, but you do a very big shrinkage, because the shrinkage parameter is between 0.10 and 0.20. Then you compute the residuals, you update the residuals, and you go to the next iteration. So the convergence, you work that until convergence that is evaluated in an independent tuning set, and it's also, there are 10 replicates for the 10 training subsets and 10 tuning sets. The important result is that R-busting approximately takes about 2% of the time of the original busting algorithm. So that's some results from González-Recio, recent results. So it will be the method to be used in the Spanish genomic evaluations. Well, I will go to the results. For the Spanish reference population, the accuracy that was obtained, well, there's the reference for the pedigree index And for the Bayesian lasso, the DGBs obtained with the Bayesian lasso or with the R-busting was quite higher than the pedigree index as obtained. The accuracy that obtained with these methods was much higher than the pedigree index as expected. And for the, in general, for the Bayesian lasso, accuracies, Pearson correlations were a bit higher. For the mean square errors, it was a little bit more favorable to the R-busting method. All of this, again, with the Spanish reference population. And when you regress the latest proofs or latest the regress proofs from the validation animals, from the younger animals, on the DGBs obtained with the reference population from some years ago, then the B-values you obtain are much favorable with the R-busting than with the Bayesian lasso. For the urogenomics reference population, the accuracy obtained, the Pearson correlations are 0.71 to 0.73, depending on the trait, so quite similar between these traits. And the regression coefficient was very close to 1. So it's some parameter that we look very much at interval because of the test, the interval test. Well, this is just a graphic representation of the increases in accuracy from coming from the accuracy in blue with the obtained with the pedigree index, then in red with the Spanish reference population, and then what we increase in accuracy with when using the urogenomic reference population. So DGBs are more accurate than pedigree index, as expected. But Bayesian lasso and R-busting perform similarly in terms of accuracy, but R-busting outperform Bayesian lasso in regression coefficient nearest to 1. The random busting showed faster computation than Bayesian lasso. That's very important for routine evaluations. And well, especially if we are thinking that we may be going to higher density chips and to be increasing number of animals in the genomic evaluations. And finally, well, the genomic reference population, as expected, increased the accuracy of genomic predictions. It's a 70% of increase in Pearson correlation against the pedigree index, and 23% over the accuracy obtained just with the Spanish reference population. So all these organizations must be acknowledged as they have contributed in different ways to this work. And well, that's all, and thanks for your attention.